before that we only had used a one cycle unit. Okay, so let's take a look at this here. Let's see how much we can advance because we are kind of already behind because we lost so much time. Okay, so this table here, it's in the lesson, right? Lesson chapter 13. And it's something that we have to refer to always to get clarity in context and how things are working. So all these timers are available in our micro. However, we'll be only working with timers 6 and 7 that don't have any capture compare channels. So they can only generate the update event. We can only work with the update event. Okay? And what is the update event? It's when the counter rolls over. Okay? And when does the counter roll over?
When it reaches the maximum.
The maximum, right? Either the maximum you can represent in 16 bits, which is 65,535, or it could be the number that we write in an ARR register. Okay? That's what the ARR register is for. So therefore, the steps to configure this, and I've gone through this multiple times, but I feel like some students are still struggling with this, which is why I keep repeating it. So the first step is to define the time tick. So how fast is the timer ticking? Okay? And that gets down through the prescaler. And the easiest way to do this is to look at the bus speed and also think that maybe ticking at 1 microsecond is a convenient number. So we also need to realize that 1 microsecond is 1 megahertz. Okay? That should be super straightforward. So therefore, if we're running at 40 megahertz, we need to prescale by 40. If we're running at 64, we need to prescale by 64. If we're running at 25, we need to prescale by 25. Huh?
I have a question. Why is 1 micro equal to 1 megahertz?
Because 1 over 1 megahertz is 1 microsecond. Frequency is 1 over Q. And vice versa.
Yeah, so you just do the inverse of your.
Yeah.
I know,
But
like,
this
micro
should-
is negative 6 and then mega is positive 6. So I don't know how that becomes.
Pull your calculator.
Yeah. But this is math 1, right?
Mm,
I mean, you should have seen this in math.
yeah.
So if you have 1 over, and then if we're running at what,
40 megahertz will be 40E6, right?
Mm.
right? So that, I mean, doing that gets us 25 nanoseconds.
Oh yeah, because that's a time tick. Yeah.
Yeah.
Yeah, but that's what I'm saying. Like, what I want you guys to keep in your brains is that 1 megahertz is 1 microsecond. 1 kilohertz is 1 millisecond. Okay, those 4 things should be super clear.
Yeah.
Okay. Once I have a convenient tick, I can say how many microseconds I want to count to generate the event. Now, in this demo that I did here, the last demo that I showed you guys,
1 million or 1 micro.
I created a function that is called set timer millisecond event. So basically, use the timer to generate a 1 millisecond event. Now, there are multiple ways of doing this. This is only one way of doing it. And what I did, I said, well, a way I can generate a 1 millisecond event is to make the timer to tick at 1 microsecond and then count 1,000 times. Why? Because 1,000 microseconds is 1 millisecond. So that's exactly what I did here. Remember that when I divide the system core clock by 1 million and I subtract 1, I have exactly the prescaler I need.
Yeah.
Because if I'm running at 40 million, divided by 1 million is 40. If I'm running at 64 million, divided by 1 million is 64. So that works always. Now, what if instead I wanted to create a millisecond tick? All I need to do is just remove 3 zeros, and that's a millisecond tick now.
Mm-hmm.
Okay? Now, in this particular example, what we did, we created this 1 millisecond event, and then we did a loop here to generate a blocking delay in milliseconds. Now, I did explain also that the blocking delays are discouraged, but sometimes we need them, especially when we're initializing LCDs that we have to go in a sequence, and that's why we need to implement some sort of function that does a blocking delay. That's the only reason. Which is why, in this next demo, 25, to wrap up finally this, because I can't get stuck the entire rest of the semester in the epic event, unfortunately. I'm going to show a different way of doing this, and this demo is a copy of the other one, except that I did the following. In the timer settings, instead of making the timer tick at 1 microsecond, I'm now going to make it tick at 1 millisecond. See what I changed here?
Mm-hmm.
Okay. Then, I'm going to generate a 25 millisecond event by putting 25 minus 1 in the ARR.
Because we count starting from 0.
Yeah. So, and then I start the counter. Now this approach is different because I'm not doing things in a loop anymore. In fact, if I make the timer tick at 1 millisecond, I can go all the way up to approximately 65 seconds, right? Because the timer can count up to 65,535 milliseconds, which would be approximately 65 and a half seconds, right? So this will give me like a good range for any non-blocking event, okay? So what I do here, and I defined a blocking defined in the top, and I know that some of you get confused with this. So I'm saying if I'm not defining blocking, I'm going to do this code, basically non-blocking. Non-blocking is just waiting for the flag, checking for the flag. If the flag is active, I clear it and I toggle the LED. Otherwise, I keep looping. The advantage of using this approach is that I can execute more code and nothing's going to get blocked. It's going to skip through this if the event is not yet happened. Whereas this approach will be blocking. This approach will be waiting here until the flag gets activated. And then when that happens, we'll clear the flag. Actually, I don't know why that one is showing up. We're going to try both. So we're going to connect the scope to PA5. And again, this is going to accomplish exactly the same thing that the other demo was accomplishing, but in a different way. Because the other demo was using the timer just to generate a 1 millisecond event, and then it was doing the count in a loop with software. Whereas this one is using the timer for the entire event. It's different. Let's run this. In the non-blocking fashion first. When we look at the camera, that I'm going to bring up right now, it shows exactly 25 milliseconds more or less. Okay? And it's non-blocking. Now if I go and I uncomment the define blocking, now it's going to be doing the blocking part of the code, which is this one. And in this part, it's just going to wait until flag gets activated. Okay? It's going to block the code there. And when the flag is activated, it's going to clear it and it's going to toggle the LED. The result is going to be exactly the same. See? No difference. Now, which one is better? Well, obviously the non-blocking, right? Unless I strictly specify that you use a blocking event, most likely we'll always like to use non-blocking, okay? And also, if we're using blocking, and if we're adding any other code to that, that thing is going to get blocked by this 25 milliseconds. So, for example, one typical thing that will happen here right away is that if we are receiving, and that actually would be a good example to revisit the USART. If we are receiving bytes from the USART, and we're sending all the bytes one after the other using the open source terminal, this thing will fail to receive the bytes. Why? Because this will be blocking here for 25 milliseconds. So whereas if we're using this one, it won't do that. Okay, so that's the difference. So we're going to show an example maybe later to revisit this demo with that. Any questions up to this point?
is blocking versus non-blocking.
Yeah, in the update flag. That's all we have so far. Because now we need to move on to output compare, because I already started discussing that with the other section. Just a theory though. Okay. Let's push this. Now, I always turn off the volume. So what is output compare? Output compare, among other things, uses the capture compare channels, which is why the basic timers cannot do output compare, because they don't have any capture compare channels. That's why we started just doing the update flag first. Now, before we talk about anything, the timer itself has a counter that is actually called CNT. In fact, if I go here, I could do timer 6 pointing to CNT. Okay? So I could definitely, here Copilot's being stupid and is saying, reset the counter. No, I don't want that. But I could potentially read the counter if I wanted to. However, it is most likely always a bad practice using a timer and trying to read the counter, because it defeats the purpose of a dedicated peripheral. The dedicated peripheral counts on its own and generates the events as things happen. And then the software handles those events. The software doesn't mess with the counter. Why? Because if you try to use a counter to do any timing operation with software, by the moment that you read the counter and you try to do anything with it, the counter might have already counted 2 more ticks or 3 more ticks. So that's going to be highly inaccurate, right? Because we have cycles. So that's why, again, we want the peripheral to perform the count and to generate an event exactly at the time that something happens. For example, up to this point, exactly when the counter rolls over, which is the update event. Now, in this output compare event that we're going to talk about now, why is it called output compare? Well, because we are comparing, or the timer is comparing. And what is compare? The timer is comparing the counter CNT against a capture compare register value that you write with software. Okay? And obviously, these capture compare registers can be named as capture compare register 1, capture compare register 2, capture compare register 3, or capture compare register 4. Now you have to be very careful, because these things are defined as a data struct, and you may be tempted to say, timer 6 pointed to capture compare register 1. Oh, it works.
But it doesn't.
But timer 6 doesn't have a capture compare register at all. See, this is a generic definition based on the data struct. So you have to be very careful, which is why this table is important. So in fact, in timer 6 and 7 doesn't make any sense to use the capture compare register.
No.
In timer 16 and 17, you only use capture compare register 1. In timers 15, you will use capture compare register 1 and 2. This one only 1.
So then,
And all this one will have from 1 to 4.
so then why not use TIM 1 through TIM 4?
Well, we wanted to start teaching you the basics with these ones first. And also, it will be an overkill. If you're using the timer, here's the way I see things. If you're using the timer just to generate an update event, use these timers. Why waste the other one? Because the other ones can do way more, right? It's the way I feel when I see people driving like super expensive cars like a Mercedes AMG at 30 kilometers an hour. Sorry, but you're tempted to say what a waste, right?
It defeats the purpose.
Yeah, well, you're not supposed to be speeding, but I'm just saying. Anyways. Yeah, so the timer can do way more, so we cannot use the resources up to the point that we need them. Now, how does this thing work? Let's do a graph here. Let's assume, and I'm running out of ink with this. So let's pretend that this is sort of like a timeline for the counter, and this is my counter CNT. That let's assume that it's counting in the full range. So it's going from 0 to 65,535, or if I want to say it in hex, from 0 to 0xFFFF. Or whatever value I put in the ARR register, right? Because I could actually make a count roll over first. So right now, the way this is working is with the update event is when the timer reaches the end and then it rolls over back, then we get the update event flag. I think it's UIFEF, right?
UIF.
Yeah. This is update event. Now we're up.
Is it UIF or UIE?
UIEF. I think it's
Update, interrupt, event, something.
flag, or is
Event
it
flag?
UE? Well, but it's something like that. I might
Yes.
have the letters swapped around. Update event interrupt flag? Maybe? We can check in the code. It's right here. It's update.
Yeah, UIF.
Oh, UIF. Oh, okay. Thank you for correcting. Update interrupt flag. Okay. So how is this output compare event going to work? This is where it's interesting. I'm going to grab capture compare register 1. Let's assume that I'm using just the first capture compare register. And let's pretend that this timer, whatever timer it is ticking at 1 microsecond. See, that's why I like you to use 1 microsecond, because that's a convenient number. Okay? Let's say that it's ticking at 1 microsecond. If I write a 200 in the capture compare register 1, what is going to happen is that whenever the CNT counter reaches this value, whenever the CNT counter is equal to 200, this is going to generate an event,
Which is your
which is my
UIF.
output compare event.
Um,
Okay? And it's going to do it automatically. So a terrible way of doing this would be you pulling the counter and saying, if CNT equals 200, do this. That would be awful. Because by the time that you start using that, CNT is no longer 200. Whereas this thing will activate the flag, the corresponding flag, automatically when this happens. Okay? That's why it's called output compare. Now, if we go into the reference manual, because we need to know how to read the reference manual. Any embedded system developer is expected to understand how to read documentation. And we've been telling the industry about that, and everyone says the same thing, that they should know how to read documentation. So make sure you get familiarized with this thing. You don't have to memorize the whole thing, just understand how to look for information. So right now, when we're looking at timer 6 and 7, we go to the registers and we go to the status registers, is where we see the flags, right? The SR register. We only see, oops, I lost it. We only see this flag, right? UIF, the one we were just talking. Why? Because this one doesn't have any other flags. But now if we go to timer 15, 16, and 17, and we look for the same register, you will be surprised. Because we still have the UIF flag, because every timer will have it. But this also has the capture compare 1 flag and the capture compare 2 flag. Why? Because timer 15 has 2 capture compare registers. If I go to timer 16, 17 that only have 1, let's do that. Those will only have capture compare 1 flag, see? Whereas the other timers that have 4 will have 1, 2, 3, and 4. That's why you got these reserve spaces here to make it compatible with the other ones. Now these are other flags like the overflow flag, whatever, that we won't worry too much about it. Okay? Questions after this?
Yep.
Okay.
Learn to read your documentation.
All right, so let's assume that we're dealing with this thing. The timer starts, the counter starts at 0, reaches 200, event happens, something happens, we deal with it, whatever. Then the counter just keeps going. When is this event going to happen again?
And the capture compare register is equal to 200.
Yeah, so that means that what's going to happen? How much time is going to pass until it happens again? Yeah, if it's set to the maximum, it's going to do the full range and come back here, which is going to give you 65. If it's sticking at microseconds, this is going to be more or less 65 milliseconds, right? So you will remember this later. So try to save it somewhere. Whenever you're trying to generate an event and somehow it's not working and it's giving you the 65 milliseconds, that's a bit of an awful number that is telling you that this thing is doing the full range and it's coming back. So it's not working the way you expected. Or maybe you want it that way. But ideally, what I would like to do here, and I want you to see the difference. How is this different from this? Well, it is different because now this event is attached to the channel, meaning that if I have more channels, I can have more events using the same timer. Whereas in the other update event, I can only have one of those per timer because each timer will have only one counter. Okay? But the problem I'm facing here, like if I want this event to happen every 200 microseconds, I do have a problem because it's going to happen at the first 200, and then what? How can I make it so it happens every time, every 200 microseconds?
Update the ARR. So like, could you just like force an upper limit for the ARR, and then it'll just force it to only do 200?
Yeah, it would be a bit tricky because if I did that, and the other thing with the problem is that if it will defeat the purpose of using multiple channels. For example, let's say if I'm using two channels, and one I want it to be at 200, and the other one at 300, then the second one, it will never happen if I reset the ARR at 200.
So then,
Because it will never reach, the counter will never reach 300, see what I'm saying?
I almost want to do a modulus there then.
Well, it's sort of like a modulus thing, but here, think about it. And this is where we need to change our mindset because we tend to change, we tend to think always in terms of software.
Yeah.
And what you need to understand that this guy is a separate entity, is like a dedicated peripheral that is counting on its own. And that is the advantage that we need to take. So if this event happens at 200, how can I make it so then it happens in the next 200? What can I change with code that doesn't affect the functionality of the timer?
You have another channel.
I could do another channel, yeah, but then eventually I'm gonna run out of things. I only have 4 channels max. Then what if I want to do this same channel every 200?
We have to configure a flag specifically then, right? We have to.
Okay, the flag happens here. Then at this point, when this flag is encountered, what do I do?
Perform the function that you're wanting it to do.
Yeah, but then how do I do it for then it happens again in the next 200? Increment what?
The channel.
This guy. What if I add another 200? So it happens at 400, at 600, and so on. Every time this event happens, I rearm this one.
By an additional 200.
Yeah. Now, what is the advantage of that? The advantage is that the timer is counting on its own. Let's say that you generate the event and you do a couple of things here in code that the time that it takes you to handle them is equivalent to 2 timer ticks or 3 timer ticks. Doesn't matter, because if you added 200, this guy is going to happen exactly at 400 again. It won't get drifted by that overhead. See what I'm saying?
So then when we have the OC event happen, we would then want a plus equals 200 to our CCR.
Yes, exactly.
Okay.
Exactly. And then it doesn't matter if your code takes a few ticks, because that's time that's going to take there, but the timer on the background keeps counting, so the time is going to be perfect. It will never get drifted. Okay? Whereas if you were doing this in software, it will get drifted because the time that it takes to execute the code will be added to the count.
Okay, so we initialize it at 200, and then when this OC event happens, we just plus equals 200. That's it. That's what it needs to do.
Yeah.
When it overflows, it's gonna automatically reset itself anyways.
Yeah.
Okay, cool.
Okay, but here's the part that I need to show you. When I'm at 65,400, let's say that I've kept adding 200, 200, 200. Then I'm at 65,400, and I add another 200.
Overflow.
Now I'm at 65,600, which is not possible, right? At this point, there was an update event, right? That I could be using or not. Again, the update flag, I could use it or I could just ignore it. Right? At this point, I'm interested in this one. Now, would this work?
No.
Well, let's find out. It's telling me that 65,400 plus 200 is 65,600, which is correct. However, here where it comes our beautiful digital logic, what happens with these hex digits? Carry down. So we only care about this one, right? Because it's 16 bits. Yeah, there's no way to save this guy. It's only 16 bits. This is 8 bits, 8 bits. There we go. So then we have a 40. A 40 in decimal is 64. So what we just said is that 65,400 plus 200 equals 64. Obviously, someone who doesn't understand 16-bit logic will say you're crazy, right? How? That's not possible.
But you're not.
Yeah, but I'll do this. 65,400. How much left to reach to the last count? Is 535, right?
So it'd be 135.
135. Then when I go from 65,535 to 0 is another count, right? One more, and now I'm at 0. At this point, I am at 0. Then I ended up at 64. How much is the sum of that?
I'm hoping it's 200.
It is 200. It is 200.
Yeah.
So then the question is, do I need to worry about the rollover? No,
Interesting.
I don't worry about the rollover. And I always say this, that
So the counter is smarter than I am. Is what it
yeah,
sounds like.
that this is the beautiful thing about the unsigned math and the constrained math that is only in 16 bits. Because again, our timer is a thing, a counter with a bunch of flip-flops, like we studied in
1550.
1550, and it's only 16 of them. So you always roll over, and it doesn't care about whatever is carried out. Okay? And it's the same thing when we do subtraction. Later on, we'll use subtraction when we do input capture. The unsigned math also works. When you do 200 minus this number, it's not a negative number, it's another positive number because it's unsigned. Okay? But what we worry about here is that the count works. So the rollover doesn't matter. All right, last thing to approach the end. Now, what is the advantage of using this? Well, I did tell you already that the advantage is that we can use multiple channels with one timer. We don't have to put a number into the ARR. We can just use the full range of the timer. And the most important thing is that now these capture compare channels are attached to an actual physical pin on the micro.
So that means we can use that to do something like when that event updates, we can do something with our
Toggle.
sensor.
Most likely toggle.
So then you'd be 4, 8, 12, 16. So you could have like a sensor network of like 20 plus sensors on this board, like given the amount of timers
Yeah.
that we have if we needed them.
Yeah, and that's what we're going to do later with PWM. But what I want to show you here is that when you go to the timers in CubeMX, because later in the other class next week, we're going to explain the details and give you a demo. Right now, I just went the concept. When we enable timer 6, nothing happens. There's no alternate function. Why? Because timers 6 and 7 don't have any capture compare channel, so therefore they have no control over the pins. However, when I use these guys, let me go reset states. Let's say I choose timer 15. I think I'm already using timer 16 somewhere. But let's say I choose timer 15 and I say, well, channel 1, I'm going to use this channel 1 as output compare CH1. Boom, there's a PC1 that appears here. So that channel in particular is attached to this pin. And in fact, I could hold control and click, and it shows me 2 other options. So therefore, there is an alternate function that can be set for that particular channel. So what? So the timer can take over the pin and do something on its own when this event happens. For example, toggle the pin. That's a very typical one.
Could be a motor.
It can actually do set, can do clear, but the one that we'll use the most is toggle. Okay? So you can make the pin toggle automatically. After you configure the timer and you make it run every 200, then the pins toggles automatically. Whereas with the other timer, we have to encode, do a GPIO underscore toggle, right? In this case, the pin will be driven by the timer. It will be taking over the pin. And it's the same thing that happens with the USART. We haven't done that, but when you are connecting the USART, if we were able to scope the pins, the TX and the RX, we will see a bunch of signals going up and down. And that's a pin going high and low, basically 1 and 0. A bunch of 1 and 0s are going, but we're not doing any GPIO toggle, set, clear, nothing. Why? Because the USART took control of the pin. This is the same idea with this. The timer will take control of the pin, and it will toggle it or do whatever based on these events. By default, the pin is disconnected, so there are registers that we have to configure and say, okay, we want to toggle. All right? Okay. Summarizing and recapping. Output compare. Why is it called output compare? Because we're comparing this value against the counter. When the value that we put here, or better say, when the counter reaches the value that we put here, an event will be generated. If we want that event to keep happening every 200, we need to do something to this guy, which is Rex very well described. We need to do this. Okay? And this is called the process of rearm.
You rearm it with a new value.
Rearm the timer so it happens again at this time. Okay? And when that event happens, the timer will be able to do something based on what we set in the control register. We will be able to set the pin to clear it or to toggle. And that's how we're going to be experimenting next week. We're going to play with that. And then the last thing that we're going to do with timer is PWM. Okay?
When is our next exam?
Oh, our next exam is going to be on week 13. No, week 12, sorry.
So next week?
No, next week is week 11. So week after.
Oh, thank goodness.
Yeah, but you guys have to work on the assignments, and I'm going to push this weekend the assignment for the timer. So I suspect that for the exam, we're going to have USART, clock, and basic timer.
Not capture compare.
No, not this. Not this.
Okay.
So next week, I guess I'm going to have to revisit a little bit the USART. So to give you guys a little bit of more insights, so you can be better prepared. Maybe talk about SCANF, SPRINF again, and all that stuff that is a bit confusing.